Hello everyone, welcome back to the next session on advanced topics in Python. In this session, we'll go through advanced concepts. So if you're already at an intermediate level, these tutorials should be really useful for you. Patience and practice is very essential. It takes a lot of time to become a Python expert, but you will master this beautiful language given the time and the effort you're putting in. A little bit about myself. I'm Anand. Um, I have been working for the last 16 years in data management, data analytics, data science, data automation. Uh, I previously covered comprehension, the use of map, filter, reduce, and zip functions, a little bit about Lambda functions, and a little bit about dunder functions or magic functions. Today's session, we're going to cover generators and decorators. Um, and the next session be the final session, and that will cover hashability. Let's start with generators. So generators are a simple way of creating an iterator. Um, so we looked at different types of iterators where we can go ahead and iterate through functions. But to create an iterator, we need to put in a lot more effort. We have to build a lot of methods that we needed, uh, like the iter method, uh, that's a dunder method, and another dunder method called next. Uh, all those things we need to do, and we also need to know when the iteration is complete. We need to raise the stop iteration, and then after that, no more values returned. So all those things need to get done when you actually build an iterator. So the generator is a way to create these iterators, but in a much more simpler fashion. So what is a generator and how is it different from a method? So the way you write your generator and way you write your method are going to be very similar. You're going to use a def statement, write it down, and like use a def statement and then put in your method name or a generator name. The way Python will know if this is a like this one is a function and this one is a generator. The difference between these two is that the function uses a return statement, um, and it has no yield statements. A generator would typically have one or more yield statements. It may also have a return statement where it terminates processing, but it need not have it. So if it has at least one yield statement, then Python knows that it's a generator type. So when you print the type of this mygen, it will actually show a generator. While you print the type of my function, it shows it's a function. So Python knows it by the presence of yield statements. And if there is at least one yield statement, then Python recognizes that it's a generator. Um, the generator function uses yield statement. So what is a yield statement? So yield statement, um, it it kind of is like a pause button. So when your function is when your generator is executed, when it finds a yield button, that's where it pauses, and whenever you call the next of um, that generator, then the value is returned, and you can keep calling next until the number of times we have stop iteration. So at the end of this, we get to stop iteration, and there's no return statement here. So if there is one, then whenever it hits the return statement, it stops iteration. But if not, at the end of the defined function, defined generator, it hits stop iteration. So if you've used xrange, like you've used the range function, um, like in a lot of for loops, when you want to go through a list or a set of series of numbers from 0 to 10 or 1 to 20, we use the range function. Uh, there is an equivalent generator that Python provides, which is called xrange. So if you've used that, you know you've already used a generator. So you might have used xrange either like for iterating through certain number ranges or iterating through a length of something. Uh, but whenever you use that, um, you actually used a generator. Range generally returns a list, but xrange, it generates the numbers on demand. So why do we go through all this struggle of building a generator when we can do this with a method to be more memory efficient? So when you talk about millions of numbers or like hundreds of millions of numbers, and you want to iterate through them and do some processing, um, for example, in my case, like what we use generators for very frequently is for reading large files. When we have huge CSV files that we get at source, say we need to read through them, um, and we need to do some calculations, keep them in memory, and then write them. So we we don't like store all the information in memory. Um, like hundreds of rows may fill out the memory. If you have thousands of rows that you read at a time, then your memory is going to be exhausted. And after that, if you want to do some calculation, if you want to do certain things, then you're going to quickly run out of memory. So that's one case where you use generators. When you need to be memory efficient, you have large chunks of data that you need to work with. You need to understand that generators are a way where you don't really go through the whole execution, but you can hit the pause button at yield, and then use that information that you have for that particular value, do whatever processing you need to do, and then move on to the next one. Um, and you can iterate through that using the next method, and you can keep calling next and until you finish and hit stop iteration. So you can do that, and that would save a lot of memory. Let's look at this simple generator function that we have here. So in this my generator function, we are whenever somebody calls this my generator generator, not a function. So it's a generator function. So as it has a yield, at first it goes through the processing of n equal to 1, and then there's a print statement. Like we would typically log this in in real life production. So say we have a somewhere we log saying that this is the value of n, and then we go on and hit like see a yield here. So it yields the value of 1 here, and then so it pauses until here. So whenever we call this, uh, this would pause here. So let me run this and show you. But before that, let's quickly go through this whatever we've done. So after that, after the yield statement, all these statements are not going to be executed, but we're just going to look at it now. It has a print statement. It has a n equal to n plus 1, and then it yields again. So there's another yield statement. Versus in a function, we do certain things and then we do a return. Anything after this will not be executed. Will never be executed because like all the times the my function is executed, it goes through this order. There's no if condition or for loop or certain things that it might skip the return. It's always going to go through and hit return. So whenever this function is called, we're going to hit return and we're going to stop. It's not going to print after return statement when we execute this. So let's try this. So I'm going to execute this, and I'm going to try using the function. So the my function is what we're going to execute. So let's try executing that and let's see what it does. So it did a print here, and then it printed the value that got returned here. So it printed 1 twice. To make it simpler to understand, let me just do so. If I change that to have to print inside my function, it first prints that inside my function, and then we return the value n. So it returns the value 1, and then that gets printed here. So when we use the function, all like processing ends after this. Let's try doing the same thing. Um, Using the generator. So when we use the generator, um, we want to go through um, like multiple times, and whenever there is a value in mygen, we want it to execute it. So here, like I'm going to run through the for loop, and if you see, the for loop has gone through mygen, and the first time it printed out inside mygen, and then it yielded the value 1. So it came here and it printed the value 1, and then it it next time in the for loop it started processing from here onwards after the yield statement, and it printed this value, and then it incremented the value of n, and then it yielded the next value. So we were able to process just the part after the first yield and until the next yield. There is no statements after this, so we don't have anything happening here. Say if we give a print statement here after last yield, and then let's see what happens if we are able to loop through this one by one. So here in this example where we had a function, after return statement, whatever we had here never got executed. But in this case, if you look at it, it paused once, it returned the value 1, and then it paused here, ran until here, and then returned the value 2 that got printed using this print statement. And after that, when it goes through the for loop again, even though there's no more yield statements, it goes ahead and execute this statement, and then it stops processing because there's no more iteration left in this generator. So that is a good way to understand how your generator works. So we are able to iterate through it. We are able to pause the function using yield statements, and we can restart the uh, process when we either call a next or when we iterate through the generator using a for loop. So let's do this uh, with using the next, and let's see what happens. So now we have a generator defined here, and it has two yield statements. So what will happen when I call when I assign a to my gen? Let me also do the same thing for my function. P is equal to my function. I'm going to try to print the function b. So anything that my function returns will be stored in b, and that will get printed here. Um, so just to separate this out, let me put in a print statement. Okay, so what happens when I call this? Or let me do this. Let me split this up. Let me do this alone. So let's just print a to see what happens when the generator happens. Remember when we read this, when we spoke about this, the generator just builds a generator object until you call next. It doesn't return the value that that is in the yield statement. So let's with that thought in mind, let's try this. So when we print a, we actually get the generator object at this memory location. When I print my function, so it it um, it goes ahead. This is just this print statement. So when we run this, it actually calls my function, and there is a print statement which says inside my function in the my function function, and then it returns the value 1, and that value is printed out here. So when you execute the function, it goes ahead and does everything, and the returned value is stored in this output. While here, this a is still a generator object, and we don't have the value that is 1 or 2 returned out. Which when we did the for loop, we were able to return it. But when you actually assign the generator over to a variable, you don't have the returned value. You still have a generator object. So that's why we save in memory. So we don't actually have all these values. Say if there are million values, we don't have all those million values stored in memory. All we have is a generator memory object, and the way we invoke it is to use the next of it. So now that I have an object a, if I execute, let me split this up into. So when I execute it the first time, it provides the value 1, and it does it the second time, it provides the value 2. There are no more yield statements, but note that it has only executed until 2. We still have a print function, but there are no more yield or return statements. So in this scenario, when we go here and do this, it prints out the statement that was there, but it hits a stop iteration. So it hits a stop iteration. So there was no more value of a that could be returned. So it did execute things after the yield statement. So it did go ahead and print the after last yield string. But after that, there are no yield statements to actually return. So it wasn't able to like return a value here when the next was called. It actually hit an error which said stop iteration. So we were unable to return any value. There was no yield statement. So that's another way you can understand how we're using next in generators. And let's see a way to use it in real life. So one way you see here is we have a list, and I want to reverse it. I want to reverse the list that has numbers 1 to 8. Let's make it 1 to 10. So I have a list that I want to reverse. So I want to call the rev function. Um, Here it's a generator function. So I'm going to call the rev function, which is actually a generator. Um, so I'm going to call it using the input of L, which is a list, and I have the list here 1 through 10, and I'm going to iterate through it until the generator is done. And I'm going to print the values one by one. So let's see how this does it. So this is a simple like for loop. It finds the length of the list, and then it iterates from the uh, length of L minus 1. So in this case, 10 minus 1, it iterates from 9. So the ninth position in this index would be this. Then it keeps subtracting 1. So uh, it keeps subtracting 1 down. So it goes from ninth position to 8th, 7th, 6th, 5th, 4th until 0, because it should stop before -1. So it stops at 0. So the 0th position would be this. So it goes through and reverses the whole list, and it provides the values. So here what we do is we yield the value of the list at that position 9, 8, 7, and so on. And here we whatever value get yielded, that gets printed here. So if we try this out, we are getting the values 10 through 1. You can note that each time, if this were a method, we would have to return the whole list back. So instead of returning uh, one integer value at a time, which the memory would store, we would have returned. So here we would have stored this into another L1, and then we would have returned, like the way we would have done it is we would define L1 as another list, and then we'll append L1 dot append, and then we'll put in this LFI, and then we would have at the end of the for loop returned L1. And here we don't do a for loop, rather we call in we would just print rev off, and we have a list there. So let's just copy the same list and use it. So this returns a list in itself. So you can see the memory that gets used is a full list. Say if there are millions of records in this list, or millions of items in this list, so that all that information is in the memory, it could easily run you out of memory. We get this information that we want back, but in this case we were able to iterate through it and just have one integer at a time in the memory. In this case we are holding the whole list, and that gets returned back. So we in the memory, the whole list of these numbers gets stored. Whenever it's like hundreds of numbers, there's never going to be a problem with your memory. But when it gets really large, depending on which server you're running it in, you will start hitting memory issues. So that's where we start using generators. Okay, now that we know generators, so just like functions have lambda functions, we can write simple generators with just a line, and these are in these are simple ways to write generators, um, and they're slightly different from list list comprehension we saw earlier because they're even more memory efficient. So the um, list comprehension that we saw was a better approach compared to the conventional approaches. But we can use generators wherever we can. In that way, like for cases where we need to just stop at uh, a value and then keep going on, the generators are a much better use of memory. So in that same lines, the generator expressions are simple generator expressions which are like one lines, but you can go through a whole list and then build the generator with it, and then so that will help us um, with respect to being uh, memory efficient. So let's look at this list. I have a list, my list. Say I want to like get the squares of each of these numbers, and if I use a list comprehension that we learned earlier, we use it like this. So we have the for loop that goes through the whole all the items in the list, and then it for each item x it returns out, or it adds to the list the square of that value. So let's say I have 5 values in it, and when I run the list, I'm going to get a list out. So this list is going to store a list with all those values. In a generator, it's the expression inside is exactly the same, but we use the uh, the brackets, the normal brackets that we use. That's how Python knows it's a generator. It's a generator expression, um, and then it iterates through that one by one. So it doesn't, just like a list goes through each of these and provides all the values, the generator expression doesn't calculate it unless it's needed to calculate it. So we look at this example where it needs to calculate it. In that case, it goes through all of them, and then when we need to do a sum, it goes through all of them and calculates everything in them, and then it comes out. So that in this case, it's going to use the same memory. Um, but in this case, so if you're just going to use the generator expression, not really going to sum it or use iterate everything. So if you look at this is a variable list, and this, if you see, it's a generator. So it knows that it's a generator, um, and it takes so the first one, we printed the list, we actually got the values back. So we got 1 square, 2 square, 3 square, 9, and 6 square and 10 square here. In this one, we don't really get a uh, list back, uh, because it's just a generator. So it gets us a generator object, which is actually a generator expression object, and this is a memory location for that. So using this, you can iterate through them using the next command, I believe, and we can go through and get all the values here. But practically, I've seen it used, the generator expressions have been used for sums and max. So if you want to find the max of this, um, so in this scenario, we see that getting used. Or you can do the sum as well. So it added all this to be 150. So it's 10 and 40 is 50. 50 plus 100 is 150. So it got that here, and we could find the max as 100 as well. So whatever we do here with generator expressions, this sum iterates through each of them, and then completes the sum when the stop iteration hits, and then it produces the result. So when we want to provide an iterable uh, list to some function, so we have our own function that we write, and we want to provide a list as an input, and that list is, if it can be written using a generator expression, this is how you use it. Let's go back to generators. The generator expression was a simpler version um, of getting that. Um, where do we use generators, right? Generators have very powerful implementation. Whenever you have an iterator to use a list, like a set, a dictionary, not a set, I'm sorry, a list, a dictionary, or a tuple, then we can use those iterators, and then we can use generators to actually work with them. So this is an example I've provided where we read a file, and then we provide a file count. But in real life, we would rather read the CSV file and do a lot of calculations. But just for keeping it simple for us to understand, I've gone through an example where we have provided, just go through them and then read the number of files and provide a file uh, like row count. So that's all we're trying to do. Getting back to why we use generators, they're easy to implement comparing to these examples. Like if we want to go through all these files but keep only one atom in memory, then you'll have to write um, a lot of dunder methods. The dunder methods you need to write are like iter. This is something you need to write, and you also need to write the expression for next. Um, so only if you write these things, you can save on memory and still make it an iterable. So you can, instead of doing uh, all reading everything and putting it in memory at one time, if you want to use iteration and then use next, like if you want to use next here, like next of the file read. So if you want to do that, you will have to write your own iterable with these dunder methods, and all those things can be difficult to do. So that's why generators are much easier to implement. Whenever you want a memory efficient solution, you don't have to write all these dunder methods. You can just do one yield statement here. That kind of takes care of iterating through your logic. Okay, so let's come to this in a minute. So that was one thing. It is easier to implement. You don't need to write those dunder methods. It's much memory efficient compared to normal methods, functions. You can represent infinite streams. So one other way we're using this is in the data engineering world, we use like streaming data. So data, um, like if you're not using like Kafka or something like that, any tool, if you want to write your own logic for streaming data, we can represent infinite streams using generators, and like we can iterate whenever you find new data, do the same logic, wait until you get the next one, then iterate again, and keep iterating it through until you have no data, and you can wait until iterate again. So you can have an infinite stream that can be represented using generators. So this is again, uh, it can be used in a lot of ways. But if you have Apache Kafka or something like that, they've already gone through all this and like taking care of the abstraction for that. You can use tools such as that, or if you need to build this by yourself, you can use these infinite streams. Then you can use generators. There's also another important implementation of pipelining generators. So that's another thing we'll look at today as well. So let's look at this example, and then we'll look at one example for pipelining generators as well. Pipelining generators is where you can do multiple generators, and you can do a series of operations. So you can do generator 1 and then pause that, go to the generator 2, go somewhere, pause that, and then uh, pipeline generator 1 again, then generator 2, so and so on. So you can probably uh, like do both of these generators at the same time. So we look at an example of that as well. So these are the main reasons why generators are very, very powerful when implemented right in Python. Okay, so again, this is an example I've kind of simplified. We don't practically use a file to just count the number of records. But say we were going to open a file that I have. In this case, there are like 9 records, and I'm going to open that file, which is called ABC, and then I'm going to like find the count of records, and then know like print it out. So I'm going to print out the number of records in that. So all I do is I go through in a for loop, and whenever there is a line, so I just add that up, and then I add that to the row count, and at the end, after the for loop is complete, I print out the row count. So if we were to do it using, so let's note this. So file like when we use file operations in Python, we use the open method. In the open method, um, we already use a pause. So whenever you use the open method, we pause operations until we go to the read operation. So we don't stop operation there. It's already like having the kind of logic that we want to do. The open already does that. And then in the like in this method, what we're doing is we are going and reading that file, and then we're splitting the file based on line numbers, and then the result comes out like whenever we call CSV reader, the CSV gen has all the records in it where we read the file and split it based on end of line, and this result will have the whole file in this result variable, and that whole file is stored in your RAM or your memory. So if your RAM is like 16 GB and your file is like 100 GB, so obviously your RAM is going to run out, and you'll the way it will happen is your computer will get stuck. You'll not be able to do anything. You'll probably have to end the processes that are running, and then after you kill the processes, that's when you'll be able to restart being able to do anything. So that's what this does. So it reads all the lines. In our case, I have like 9 records, so which is going to be pretty easy to read. Say let's add one more record and make it 10. Have 10 records. Say we have 10 million records. That's when this logic is going to throw problems. But let's run through this. What it does is after the result is produced, that gets returned to this variable called CSV gen. So the CSV gen has 10 rows in our example, and for each row it goes through and counts the row, adds to the row count, and then at the end we print it out. So in this scenario, we go through this whole file, put everything into this memory, into this one variable called result that gets returned over to CSV gen, and then that is get iterated for each row in this for loop, and then we keep adding this. So if you look at the memory operations, it's huge. The same thing can be done using a generator. Let's look at that. So this is a generator. So the same CSV reader, I'm doing the same thing. I'm taking the file name as input, and I'm going through the row, and I'm doing an open file. So as I said, the open file keeps it open until you actually explicitly close it. So for row and open, file name in read mode. Yeah, I didn't give the read mode here, but that's all right. So for row in open of file name, and then it yields the row. So it yields only one row at a time. So the only thing that gets stored in this memory when this is called. So when this is called, this calls CSV reader, and then this only returns the generator object. So this only has the generator object. So in this case, there's only the generator object here. And for row in CSV gen, so this keeps calling the next each time, or does the equivalent of calling the next each time, and it produces one row at a time. And in memory, this is just a generator object. This just has one row at a time. So we don't have the problem of storing all the 10 records in CSV gen, or in another example, tens of millions of records in CSV gen. So in this example, it does the same thing, and it produces the same row count. The only difference is this is a much smaller object, and if you want to print the type of this, um, it has a class generator, and I don't know if we can print CSV generator itself. So it is a generator object of the class, like generator object of this CSV reader at this memory location. So we get that information as well. So we spoke about pipelining. Pipelining is where we have two different generators, and we use them in sync. That is, one of the generators, generator 1 calls generator 2. So generator 1 hits the pause button, calls generator 2, and then that generator again, when that hits the pause button, it goes back to generator 1, and until it needs to call generator 2 again, it executes, and then it calls generator 2 again. So that is kind of what is pipelining. So in pipelining, what happens is we define two different generators, both have yield statements. So the first one is the internal one that we call. So here we are calling this generator 1, then that, and then we have the square as the outside, and then that gets summed up here, and then we're printing the whole thing. So we want to be able to go through Fibonacci numbers until 10. So in this scenario, what happens is it calls Fibonacci numbers of 10. So here x and y are starting at 0 and 1, and then we are going in range of numbers and then we're doing x and y. In y we store, in x we store the value of y. So and then in y we store the value of x plus y. So this way we are now producing the next two values of the Fibonacci series, and then the new value of x gets yielded out. So when this gets executed the first time, um, so um, so we're doing range of nums. So we're doing the first 10 numbers of the Fibonacci series. So we should start getting like 1 and 2 and 1 and 1, I believe, sorry, 1 and 1, and then 2, and then 3, and so on for the 10 for 10 numbers. So because it's doing range of 10, we're going to get 10 numbers. So what happens is that after the first number is returned, it calls a square generator function, and that has another for loop inside it, and it goes through each of these nums. And so at this point nums is at 10, so it goes through until 0 to 10. So the nums has any numbers in it. So we're returning this Fibonacci, this yield first time returns 1. So it goes through for number in 1, and then so it has a number, so it executes the loop, and then it goes through and squares it. So this for loop doesn't actually iterate, but it checks if this nums has a value, and each time it will have only one value because we stopped at a yield statement, so it executes it only once. So let's put in some print statements so that we see what's happening here. I should do it before the yield statement, and I'm here going to do it. So when we run this, we're going to get a sum of the square of all the Fibonacci numbers, the first 10 Fibonacci numbers. So if you look at it, what happened is we called the Fibonacci, then the square, then Fibonacci, then square. So each time it called only once because it just checks if there's a value in nums. And nums is what, this may be a little confusing. Let me say in Fib. So the square, input of square is the output of the yield value from this Fibonacci series. So that let's call that Fib. That gets passed on, and if there's a value in Fib, it squares it, and then that gets yielded out to this function that is summing all the values. So the sum will take the first value that came out from Fibonacci series and got squared, and then next time another number, the first number would be 1, the next number would be 1, and then the third number would be 2, and so on. So it gets it gets added each time. And let's also print the num here. So before squaring whatever the number is, we can see it here. Let's do that. If you look at it, it was 1 first, then 1, then 2, then 3, and then it squared all these numbers up, and then it returned the output of 4895. So the first 10 Fibonacci numbers end in 55, so we get a We get a square of all these numbers, 55, 34, and all those numbers. Add those up, and we get this sum. So that's how we use pipelining generators. So those are all the concepts in with respect to generators. Let's look at decorators. Decorators are a design pattern that you can add new functionality to an existing object. So you already have one method. Say you want to do something to that method, but you don't want to really go in and change it because like you have some logic that needs to be done at multiple places, or it's not core to the functionality of that method. So in that case, it's you can use a decorator. So the way we use a decorator is by writing a method. So this uppercase function should be a method. So it's a function. And we've defined that function here. And that function takes another function as input. And then we have a wrapper that does what we need to do. And then we execute this. So when somebody wants to execute this function, if we write above its definition these at the rate and then write the name of the method that you want to decorate this method, so this would become a decorator. Whenever you write this, this becomes the decorator and it decorates this method. So it decorates this method. So whenever somebody calls the say hi function, it would actually be decorated by this. So we would actually do this, and then so this part will be executed first. The uppercase decorator will be executed first, and then we will do this. So let's look at this. Let's try looking at what this decorator function does. So when somebody calls say hi, it looks at the definition of say hi. It's here, but there's actually a decorator function that needs to get executed before. This say hi function just returns hello there. But before I do that, I need to check what my uppercase decorator does. So let's go up and look at the definition of uppercase decorator. So the uppercase decorator has another wrapper function defined under it. And this uppercase decorator returns this wrapper function. So it actually returns the whole function wrapper, not a variable. It returns the whole function wrapper. And what that wrapper function does is it takes our function that is input, and then it calls the upper function, and you has the variable name make uppercase, and then it actually returns the make uppercase variable. So that's a little bit a lot to take in. So I will just kind of say it in some other words. So what we do here is whenever somebody calls the say hi, it calls the decorator, and the decorator has a like function as its input parameter, and that function is referenced in the wrapper, and the wrapper is what is returned back to this. So what that would do is, if you look at this, all we do is we make the function and we call the upper method. So let me define this first, and then we'll try running this. So in this case, when I have a like decorator defined, it actually change this hello there into the uppercase, and then that's what is returned here. And when we print it, it actually prints the uppercase of hello there. If we when we go back to the definition and take this out, at that case we're going to get this without any decorator logic being run. So it's going to go here. So if you want to add print statements to see what this exactly is doing, let's do this. Let's add print 1 here, and then let's do print 2 here, and then let's say print 3 here. So let's see how, in which order it executes it, and then let's say print 4 here. Let me I want this decorator to be executed. So let me say, yeah, let me say print 4 there. So in what would happen is, because there is a decorator here, even before getting into into the return statement, it has to go through the uppercase decorator first. So let's see what how it goes through the logic. If you see what it does, so it goes ahead and prints this, and then there's a return statement. That return statement has a wrapper. That is actually a function that is defined here. So what it does is, at first it prints this, and then it goes ahead and before it runs the return statement here, it runs the print 4 statement, and then when it goes to the return statement, um, it it goes ahead and calls the function that we need to call. Pause for a second. Okay, so let me make this. I just added another print statement here, print 1.1, and then I changed this to print 1.2 to rather understand the flow of the logic better. So whenever this gets started, it actually has to first do the decorator. So it goes to the decorator. So the decorator, what it does is, so the decorator takes care of calling our function. So the method that gets passed here is say hi. So the say hi gets passed here. At first, the statement that it needs to execute is a print statement. After that, there's a definition of the method, so it's going to ignore this. It's just going to not process it at this point. Next one it does is return wrapper. And the wrapper is actually this function. So it returns this wrapper, and this wrapper, what it does is, it does a print 1.1, and then it calls our function that gets passed. So that would mean it calls the say hi function here, and then it after it calls this function would actually print this number 1.2, and then it will return hello there, um, and then whatever value that is there in func would be hello there, in lowercase, and after that, because this func contains hello there, that dot upper would make it uppercase hello there, and then it will print 3, then that gets returned over here. So when we actually call this, it goes through these steps, and this hello there gets returned here, and then these steps get executed, and when we actually return this, this has hello there in capital letters. This is what should get returned here. So let's try that out here. Let me compile this. Hope we're not running into errors. So if you see that, that's how it's happened. So first it goes through print, and then it ignores this definition, goes to return. The return actually calls this function, and this wrapper function first prints 1.1, then goes ahead and calls our function, which is it calls say hi, and then and after calling say hi, it prints 2, but it stores the value function hello there here. Let me also print function here so that you kind of follow along and see what's happening here. And then let me print this as well. So I'm going to do this and a few more print statements. So after that, the function here that gets printed, it has the lowercase hello there, then the number 2, then we have this uppercase, it's supposed to have uppercase hello there, and then it prints the number 3, and then we get the value here. This is what gets returned when we call say hi. So we get the value hello there in uppercase. So this is how so when we write these decorators, we need to write these wrapper functions, and these wrapper functions like take in this function, and then it takes care of calling the function and doing things around it. So we can change the values or change the output, and then we can return whatever value we want, or we can just use it for logging, which is where we use it all the time. Okay, so we are past the time today, so I'm going to quickly wrap up whatever we knew about decorators, and then we'll go ahead and end today's session. But these are the things we'll cover in tomorrow's session. We'll talk about accepting arguments, defining general purpose decorators, and then we look at what are the use cases why we will use decorators. I just want to use this and stop here, but before that, we covered generators and decorators today. Decorators are used a lot for logging, execution time measurement, synchronization I've never used. It like I've read that it's being used in authorization in Python frameworks such as Flask and Django. I don't use those much, so I'm not an authority who can talk about it. But thank you so much for joining today's session. I'll talk to you tomorrow with the final session. Thank you.